In this video we're going to take a look at why have we been bothering with all of these ways of finding the slope of different functions, the methods we discussed, the constant, sum, difference, chain product and quotient rules. So here's why. We're going to use the first differential of any given function to find what we call stationary points or turning points. With this simple function, f of x is equal to x squared, and a curve that we are all familiar with, we've studied quadratic curves in quite some depth, it should be clear that down here we have a stationary point at the vertex of the curve. Here we have a negative slope, here we have a positive slope, and between the two there's one point where the slope becomes equal to 0. It's a flat line across there. And with x squared, we also know that that's going to be at 0. If we differentiate x squared, so if we take dy by dx for x squared, okay, what we get then is 2x. 2x represents the slope. It is a straight line going through the origin. And if that does represent the slope, what we want is to try and find the point where the slope is equal to 0. So 2x equals 0. And sure enough, we find that that's going to give us x equals 0. So we know that for the function x squared, that the stationary point is at x equals 0. For different. So that's the first part. That's what we use the first differential for, just to identify for ourselves where the stationary point is. The second part of the problem is, how do we know, if we haven't been able to draw a graph, whether the stationary point represents a minimum, which it does here, or whether the stationary point represents a maximum, as it does here, for the function f of x equals minus x squared. For this function here, right, the differential dy by dx is equal to minus 2x. And it's the opposite looking line to the one over here. Once again, however, if we set that slope, that differential, equal to 0, we find that x is equal to 0. So the stationary point for both of these curves is exactly the same. The second differential allows us to say whether any given turning point, this one here or that one there, is a maximum or a minimum. So how does it do that? Well, the whole point of using dy by dx is we assume that the x value gets a tiny nudge in that direction, okay? But we make that nudge very, very small. So what happens is, if we are looking at the point here, the stationary point, what we want to know is, if we look at that very, very carefully, is that slope starting to go up over, or is that slope going down over? And we find that out by actually taking the second differential of the function. We find the point where it's 0. The second differential will tell us at that point, is the line starting to go up, in which case we must have been at a minimum, or is that line heading down, like here, in which case we were at a maximum. So the second differential is basically you take the first differential and you differentiate it again. So when you do that for here, okay, what you get is the answer 2. Over here the second differential is minus 2. This value is positive. This value is negative. It tells you that that slope is going up as you leave the stationary point, and this tells you that the slope is going down as you leave the stationary point. And that confirms our idea that for this curve we are at a minimum and we start heading up, and for this curve we're at a maximum and we start heading down. And that piece of theory, okay, applies to any function that we wish to work with. We take the first differential to identify any stationary points, and then at that stationary point we take the second differential to see whether it's heading up or heading down immediately after we have identified the stationary point.